Okay, these are notes on equilibrium and something called Le Chatelier's Principle, which is credited to a Frenchman named Le Chatelier. And it is chapter 18.2 in your book. Chapter 18 deals with reaction rates and equilibrium. We're really going to be looking at the equilibrium part. But you do need to know a little bit about reaction rates. It's hard to understand equilibrium without thinking at all about reaction rates. So reaction rates are in chapter 18, section 1. You don't need to go into that in detail, but certainly those of you who are interested in really understanding a topic, you might want to at least glance through it, get a couple ideas, understand what reaction rates mean. Because when we're talking about reversible reactions, as you learned on Friday in the straw activity, that being at equilibrium means that the rate of the forward reaction equals the rate of the reverse reaction. So it doesn't mean that the reactants or products are at equal concentrations or equal amounts. What it means is that the forward reaction is proceeding at the same rate as the reverse reaction. And as you may remember, this is the symbol we use to denote a reversible reaction. So when we're talking about the forward reaction, we're talking about this direction. When we're talking about the reverse reaction, we're talking about that direction. And reaction rate, obviously, is how fast the reaction is proceeding. So some reactions happen very quickly. Obviously, the ones I give you in class happen a lot more quickly. Some reactions take thousands or millions of years to happen. And so they proceed a lot more slowly. But as I said, one more time, at equilibrium, the forward reaction is proceeding at the same rate as the reverse reaction. So in this reaction that we're going to deal with throughout all these notes, we have 2 SO2s plus O2 yields 2 moles of SO3. And so here would be the, and we'll say, okay, here's the left side of the reaction, here's the right side of the reaction. Okay, that's just direction, but I think I said to a lot of my classes, I'm dyslexic, so I have trouble with left and right, so I'm just going to put the letters in. So here's the left side of the reaction. As you can see, we have the SO2s here, SO2. We have the O2s here, and if you count it up, you'll notice that there's a 2-to-1 ratio between those for the 2 to invisible 1. That's not at equilibrium. And then here's SO3s, so obviously we have the SO3s. And if you notice, those SO3s are a 2-to-1 ratio with the O2s from the left side and a 1-to-1 ratio with the SO2s, also not at equilibrium. But when this reaction is at equilibrium, there are some SO2s. So here are my SO2s. There are some O2s, and notice those SO2s are in the same ratio to the O2s as they were over here, so it's still a 2-to-1 ratio, and then some SO3s. But now notice the SO3s, there's 1, 2, 3, 4, so there's twice as many SO3s here as you would expect in this kind of 1-to-1 ratio with the SO2. So here, there's 6 SO3s. Here, there's 6 SO2s. But here, there's 2 SO2s, and there's 4 SO3s, meaning there's twice as many. We would say that this reaction favors the products, meaning at equilibrium, you're going to have more of the SO3 in terms of a ratio than what you have on the left side here. And some reactions favor the product so strongly that you can barely even detect any reactant still there, even though it's at equilibrium. Some reactions favor the reactant so strongly it almost appears like the reaction didn't happen. And we're going to talk not these notes but the next notes about something called it's called the KEQ. So it's a value we give to reactions at equilibrium that will tell us, are these really products favored or really reactants favored or somewhere in the middle. All right, so let's look here at two things. And this is going to be not review, but graphically looking at what we already know. So rates and concentrations at equilibrium. So as we said, the rates at equilibrium are equal. So right about here on these graphs is where we reach equilibrium. So at the beginning of the reaction, the forward rate obviously well exceeds the reverse rate. In fact, the reverse rate should be 0 at the start, right? Think back to the straw lab, or the straw activity. At the start, you had nothing in the reverse beaker, or the products beaker as we called it, so there was no reverse reaction. At the start, there was only the forward reaction, and that, for a while, well exceeded the reverse reaction. But over time, those two evened out. The forward reaction decreased, the reverse reaction rate, I'm talking rates here, increased, and at some point they were equal rates, and that's equilibrium. Compare that to the amounts. Now, this reaction is a product-favored reaction. So this graph is for a product-favored reaction. So again, at the start, there's reactants, no products, but as time goes on, at some point those are going to be equal, okay? But then we keep going, the rates keep changing, and it's not until those rates are equal that we end up with equal, not equal amounts, but non-changing amounts. So at equilibrium, there's, this concentration or amount of your products, there's this of your reactants. And as I said, this is a product favored reaction, because in the end we end up with more products than reactants. We could, certainly draw a line like this maybe, and then a line like that, say, and that would be a reactant favored reaction. So there are two kind of graphical representations of both rate and amount at equilibrium. So let's look at Le Chatelier's principle. Le Chatelier's principle is all about reducing stress. So for those of you who feel stressed out by chemistry, this is your principle, because Le Chatelier is all about reducing stress. And to put some words on it, what that means is if a stress is placed on a system in equilibrium, the equilibrium will shift to counter the stress and reestablish equilibrium. That's a lot of words, but it essentially says if there's a system that's in equilibrium, and let's say just in general in balance, and there's some kind of stress that screws up the balance, that and this actually should say the reaction will shift. I don't like using equilibrium there. Let's say reaction. That the reaction is going to shift until equilibrium is reestablished. So what that means, let's take this in a human analogy. If you're in equilibrium, you're in balance, everything's going well, you've got your homework done, you're done with your sports practice, you've done your chores, everything's in equilibrium, and then you're given a stress, oh, you didn't realize you had notes to take for chemistry tomorrow, your friend just texted you and said, dude, did you take those notes? Okay, there's just been a stress placed on you who was in equilibrium. So now your reaction needs to shift to counter that stress. You need to take those notes so that you can get back to equilibrium. Otherwise, you're going to be stressed. So let's go back to this reaction that we had. 2SO2 plus O2 reacts to form 2SO3. Now, let's say we add something. Let's say we add some SO2. Okay, so we're going to say plus SO2. What do you think is going to happen if we add SO2? And here let's put in, this goes left, this is right. Is the reaction going to shift to the right, or is it going to shift to the left? So once you've thought about that for a second, you can certainly pause the video. Think about, how is this reaction going to shift? Now we have more of this. Think about, again, if you're done with your homework and you get more homework, your reaction is going to shift to decrease that homework, right? How's that going to happen in real life? You're going to do the homework. In the life of a reaction, you're going to shift away from the thing that was added so that you can get rid of that thing that was added. So we're at equilibrium. If we go back to here, that's like being here. And now we're going to add some more of this reactant. So that would kind of go up like this. That's now going to shift this up as well. Because at equilibrium, the relative amounts, whether you have more or less, but the relative amounts should be the same if you have an equal rate. So what we say here is if we, and let me kind of erase this so that you can see better. If you add a substance to either the left side or the right side, the reaction is going to shift away from the addition. So if we add some SO2, we're going to get the reaction shifting to the right. That's a way we could get more SO3. Same if we add O2. But if we add more SO3, the reaction is going to shift left because it's going to want to shift away from the SO3. So what would happen if we were to subtract some SO2? Go ahead and kind of come up with your answer. If we subtracted, we do minus SO2. And again, it might help to look back at your graphs from before. If we remove a substance, the reaction is going to shift towards the removal. So if we're taking some of this out, then the reaction is going to shift in the reverse direction or to the left. Same if we took some O2 out. If we took some SO3 out, then the reaction is going to shift to the right. So let's say we're trying to produce SO3, and we get some, and we have a way of removing that from, say, our beaker or whatever, then we're going to produce more SO3 because that equilibrium is going to want to shift right to reestablish itself. All right, let's look at Le Chatelier's principle and temperature change. So here's our reaction. What I want you to do is look at a heats of formation table that you have and calculate the delta H of this reaction. So you can pause it and do that. So you should have gotten 2 moles times negative 395.7, that's the heat of formation of SO3, minus 2 moles times negative 296.8, that's the heat of formation of SO2. I didn't even put in the plus 1 mole times 0 because it's obviously 0. And that gives us a delta H of negative 197.8, making this exothermic. Okay, that's all review. But now I want you to think about the reaction almost written like this. If it's exothermic, we're getting heat as a product. And so we can rewrite the reaction like this. 2SO2 plus O2 forms 2SO3 plus heat. We're getting energy out of this reaction, which, by the way, explains a little bit about why this is a product's favored reaction. So now, let's talk about what effect temperature change is going to have on this equilibrium. So let's say we add heat to this. So we're going to increase the temperature in which this reaction is taking place. We're going to heat it. We're going to put it on a hot plate. Is that going to favor the forward reaction or the reverse reaction? Use what you just learned about adding reactants and products or removing reactants and products using heat as almost a substance. Okay? So what some of you may have realized is that if you increase the temperature, that's going to favor the reverse reaction because it's going to drive the system away from the excess energy. This system already produces energy. It would almost be like adding a product. And so it's going to favor the reverse reaction. If we decrease the temperature, we put this in an ice bath, that's going to favor the forward reaction because you're taking away a product, and so it's going to go towards the product to replace that product. Now let's look at Le Chatelier's principle. Should really be, well, we say the Le Chatelier's principle, I don't know. And volume change, okay? So we're changing the volume of the container. The first thing we need to go back to is that we need to remember that volume and pressure are inversely proportional. We're remembering this, of course, from gas laws. And so this is also, we can look at pressure change. So we can even say like /P for pressure. Now, obviously, when we're talking about volume change, if we're talking about volume and pressure being inversely proportional, we're not talking about an open 250 milliliter beaker and then we're putting it into an open 400 milliliter beaker. That hasn't actually changed the volume of the substance any. All it's done is put it in a larger container. So we're talking about changing the volume of the substance. So let's examine this equation in a little more detail. Over here we have 2 moles of SO2 and an invisible, but we'll put it in 1 mole of O2 for a total of 3 moles of stuff on the left. Look, I didn't even have to put in my little L. And on this side we have 2 moles of stuff on the right at equilibrium. So there is, or just in general, sorry, not necessarily at equilibrium. So we have 3 moles of stuff here and 2 moles of stuff there. So what do you think increasing the volume, which would decrease the pressure, or decreasing the volume, which would increase the pressure, how do you think that's going to affect things? You can go ahead and pause the video, think about that, or look it up in your book. So if we increase the volume, that means we're decreasing the pressure. So volume increase, or squeeze it in here, pressure decrease. The volume is going to shift backwards because it's going to shift towards the greater number of moles, because now we have lower pressure, bigger volume, so we can have more moles. However, if we were to decrease the volume, which is going to increase the pressure, the reaction is going to feel kind of crunched almost. So it's going to want to go towards fewer moles. If you have too much stuff, say you have too much stuff in your room, you want to clear some of it out. And so in that case, the volume or the reaction is going to shift forward because that's where you have fewer moles. That one I think is a little harder to understand. So, take a second to think about that. Let's take a different reaction though. Let's take this reaction. HCl liquid, oh, this actually should be aqueous. That's a mistake. Both of these should be aqueous. I mean, it doesn't matter, they can be liquid, but that would be some awfully concentrated stuff. So I'm gonna switch both of these to aqueous. Sorry, my mistake. So aqueous HCl plus aqueous NaOH yields liquid H2O plus aqueous NaCl. One thing to note is the H2O is not coming from the fact that these are aqueous. As I said, they could be liquid, but boy, that would be some really strong stuff. So it's coming from the fact that this is a double displacement reaction with the H and the OH. But my point being, there are on this side of the reaction 2 moles, and on this side of the reaction, there are also 2 moles, which means this is a time when at equilibrium, if you are to change the volume or the pressure, it actually doesn't affect the reaction at all because there's the same number of moles on either side. It's almost like, say you have one of those sinks in your kitchen, which is actually like a double sink. There's, there's like one sink and then a little divider and then there's another sink that a lot of people have, and a lot of people have like dirty dishes in one, and as they clean them, they put them into another or whatever. But let's say you have too many dishes in one and just a couple in the other, you're going to transfer dishes until they're kind of equal. Now, here we're looking at equal amounts, and as we know, that's not what equilibrium is, but you kind of get the analogy. Versus if you have equal amount of dishes in both sides, or here's a better. Okay, you've got your double sink. kind of making this up on the fly. But you've got your double sink, lots of dishes in one, a few dishes in the other. You're going to start working on the sink that has more dishes. You're going to start washing those to shift away from that huge amount of dishes in one, okay? Versus if you have the same number of dishes in both, same number of moles in both, then changing that isn't going to change. I don't know that this analogy is holding up. It sort of worked in my head, but the point being, if the volume, if there's the same number of moles on both sides of the reaction, then changing the volume or the pressure doesn't actually change the equilibrium. It doesn't shift the reaction forward or backward because there's no way to relieve that stress. I guess that's where I'm going with that. If you have a sink of dirty dishes and you want to relieve that stress of the dirty dishes, and yet your other sink is just as full, it doesn't do anything to move them from one to another because there were the same amount in both. So there's no way to reduce that stress. I think the problem I'm running into is I'm trying to make an analogy of stress as something we feel versus stress in a reaction. I don't know that it totally holds up, but hopefully that makes sense. All right, if you have questions, feel free to put them on the comment section or ask them in class.